We have another returning Roguelike Celebration speaker from more recently than 2016, but we have Brian Cronin, an engineer and designer who just can't stop making roguelikes. He spoke at Roguelike Celebration 2021 about Monster Train, a deck building roguelike, which I'm quite fond of, and has been, after starting on pre-smartphone game development, has been working in games professionally for 20 years, works full-time in the educational game space, and works in roguelikes in his free time. He's passionate about gameplay architecture, game design, board games, comedy, and Twin Peaks. And you're here to talk about architecture, one of my favorite topics.
Awesome. Well, thanks for that intro. I wish I could talk for half an hour just about Twin Peaks, but maybe not the right conference. I'm here to talk about gameplay architecture, and specifically I'm going to talk about a technique called black box sim. I'll get into it, but this is my beautiful artwork of what the black box sim is. Let's dive in. I'm getting over sick, getting over being sick, so I might cough a little bit. I apologize. Hello, my name is Brian Cronin. I'm a game engineer. I've been working for about 20 years in the game industry. These are some of the games I've worked on. Roguelike wise, I did Monster Train in 2020. Inkbound I contributed to for about the first year or so. It's kind of a multiplayer cooperative roguelike, pretty interesting. And that one came out in April this year. And then I'm also working on, in full time, I work on this game called Dojo Islands, kind of in the educational space. And I'm working on my own roguelike game called Slumber Realm right now, which you won't find much of on the internet yet because I'm not good at marketing. First I just want to talk about what is gameplay architecture, just to explain what I'm talking about specifically. It's a series of patterns we use to construct gameplay. It's kind of vague, but it's not game engine architecture. So I'm not talking about how we organize vertices to render them or collision detection. Those are all useful primitives that you need in order to construct gameplay, but I'm talking about gameplay itself. But the constraints of a game engine can definitely influence gameplay architecture. So all of these games here follow different types of architecture to support the wide array of gameplay that is available. How you structure a first-person shooter like Doom is very different from a real-time strategy game or a turn-based roguelike. But before digging into the theoretical architecture talk, it's always important to remember what's most important, and that's, of course, delivering value to stockholders. Maybe not the right sentiment for this group, so let's say making a fun game for players. And building your game on solid architecture will massively help you achieve that goal. So if we build our game with great architecture, what does that get us? What's the benefit? Determinism. This a whole host of things can depend on your game being deterministic. That just means the same inputs will result in the same outputs. So if you have really great solid architecture, you can achieve determinism, which is really great. Save, load, and networking. I'll go into these. I don't have a half an hour, so I can't go super in depth on these topics, but I'll explain how what I'm proposing here benefits you and makes it much easier to implement save, load, and networking. I would never say that it's easy to implement these, but much easier. Backwards, okay. Replays. So whether you were talking about player-facing replays where a player can rewatch what they did, or even developer-facing replays. We did this on Inkbound, where we had a system that a player could send us a replay file. It was even automatically sent to us in many cases. And we could replay their gameplay and reproduce bugs. An undo-redo system and a preview system, kind of related. You might have a game where a roguelike where the player can undo their entire turn, or maybe they have an ability to undo a certain action. Or a preview system. A lot of roguelikes are doing this now, where you're going to play a card in a deck-building roguelike, and the player wants to know what is going to be the outcome of playing this card. We did this in Monster Train. And it was very difficult to implement because we didn't have really solid architecture for that game, which I spoke about previously in 2021. So much easier to implement these types of gameplay systems on top of solid architecture. Much easier to test your game if you have great architecture at the foundation. So whether that's through automated testing or even enhancing manual testing, there's a lot of things you could take advantage of. And all of this leads to fewer bugs and easier reproduction of bugs. I could speak about this subjectively with my own experience of working on this style of architecture that I'm proposing, and before and after, much easier to reproduce bugs and much easier to fix them. But it's worth pointing out that there are times when you don't need to like go nuts with gameplay architecture. If you're doing throwaway prototypes, game jams, if you're doing some learning project, you're just trying to learn some new programming technique or game genre or whatever. But all of these have something in common. Oh, by the way, shout out Pig Squad here. This is a picture of the Pig Squad in Portland. Great group. These all have something in common. These are all a small amount of time. You're talking about a few days that you're working on a project. Then I don't think it's super important to spend a lot of time thinking about architecture. But if this is more the schedule you're looking at, which even for some smallish roguelike games, you might be looking at a schedule like this. I could speak about this, personally. It really benefits you to consider your gameplay architecture. So in 2021, I spoke about Monster Train, currently wearing the shirt that Marlo designed for that one. And in that talk, I presented this very vague concept of a model view controller. That might mean something to some people here, but just his proposal of how we can separate our game logic from presentation, UI, etc. Let me do a cough. Okay. So I wanted to go more in depth on this with this talk, with more specific implementation details. And since then, this technique has been used several times pretty successfully. So Inkbound was built with this architecture. As I said earlier, it's kind of like a multiplayer cooperative roguelike, tactical. I worked on this game called Everseed, which is a tower defense game that used this technique. And my new project Slumber Realm uses this technique. I've also spoke to a few other developers who are implementing, I wouldn't say the exact architecture I present here, but pretty similar. Wonderbelly, who previously did Round Guard, their new game is using this kind of architecture, and a couple of other developers are also using it. So let's talk about the principles. There's 4 principles kind of guide this architecture. The first is to avoid reentrant code in most cases. Now I'll describe what that means. So let's imagine we have a card game. Slay a Spire, Monster Train style game. Now, at the bottom here, you see there's an upgrade that says, when taking damage, discard the top card of the deck and apply 10 damage if it costs 0. This is just the type of effect you'd imagine seeing in a card game like this. So let's say I play a card. So this card manager plays a card. It tells the damage manager to do, damage, whatever. The player takes damage. That tells the upgrade manager that damage was applied, and this upgrade manager applies this effect. So we discard the top card, and then we conditionally apply the damage. What you'll notice about this, if you just focus on the arrows, they're kind of just calling all over the place. It's very like spaghetti-like in nature, just to use a random metaphor. So there's no concept of ownership. Everything that we started here at the card manager playing the card, and the upgrade manager is eventually calling back into the card manager to discard that card. So these arrows kind of go everywhere. The code is able to re-enter, so there's no concept of ownership. Avoid global state and singletons almost always. I'm very strict about this in my own code. A lot of other developers I work with aren't. But I found that this also leads to architecture that's very hard to maintain, and it's hard to take advantage or to get some of those benefits I said at the start. So just to make it more concrete, here we have a real-time strategy game. We have a barracks class here, and in this update function, after a certain amount of time of training, we tell the unit manager to add a new unit. And we don't really know what's happened here. That could call back into the barracks. It could call anywhere else. We have no control or knowledge of what's happening after that point. And I have noticed in practice, this leads to code that is very difficult to maintain, and it becomes hard to get some of those benefits like replays, networking, etc. And this is probably the most important principle: strict separation of data from state, from logic, and from presentation. So let's go to this kind of diagram. So data, pretty obvious. It doesn't change. It's usually loaded from a hard drive, could come from the network, piece of data. State, so it changes often. It's stored in RAM. Let's go back to the real-time strategy example. We have a tank that's defined in data. We have our light tank, whatever. It has 10 hit points. When we load that in the state, now we might have 10 instances of that tank moving around the map, and they might have different HP values. One might have 7 or 4 or whatever. Logic operates on the state. So this is player and system driven. That means the player might press a button. The system might decide that every 10 seconds, all tanks take 10 damage, whatever. And then presentation. So that is driven by, in some cases, the state or logic directly. And it's UI that shows the player what's happening. So it's animation, 3D, 2D, whatever, VFX, sound, all of that is just informing the player, telling the player what happened. So we want to keep each of these boxes as separate as we can, and the interfaces between them very strict and clear. Finally, top-down control. It's kind of related to the re-entrant code. So in this example, we have a button on the screen to damage a unit. So you might have an input system that detects when the player clicks the mouse in a region. And the UI system determines that a button was pressed, and that informs our black box sim that the player wants to apply damage to a unit. You'll notice that this all kind of flows top-down, and there's never a case where we're going to call back up. So the black box sim will never need to communicate with the UI system or the input system. It all flows in one direction. So the source of these principles is just 16 years of putting together kind of shoddy gameplay architecture and learning from that. And these are the principles I focus on. So a couple implementation notes. I'm using C# and Unity. That's what I do my own game development in. But this is more of a concept that you could apply to any language or engine. So don't get too hung up on that. And the examples here are for a turn-based game, but it works similarly if you have a frame-based game. I mean, like a game where you have an update loop. You could adapt these techniques for that style of game as well. I've done that in the past. So, okay, so here we have our black box sim. Let's get into it. When I talk about the black box sim, I'm talking about this region of our chart. So I'm talking about the state and the logic. You could think of the black box sim as an API. So we give the black box sim our inputs that are generated from the player. We don't know what happens inside of that black box, and we don't really care. And it gives us outputs that then we drive our presentation with. So that's kind of the mental model to think of. And there's very strict inputs and outputs to our black box sim. So it expects a very specific kind of format to give our inputs, like a well-structured API might, and it gives us outputs in a very predefined, structured way. So we're not poking at it from every which way. Oh, I should mention at this point, Inkbound was developed in this way, and one of the cool things we were able to do with it is the game server ran that black box sim without Unity at all. So the game was written in Unity, but we were able to isolate our black box sim to be just a pure C# executable. So we were able to run that black box sim within the Unity runtime, or just in a, think of like a terminal window, a C# program. And as a result, it was able to run really efficiently on Amazon EC2 instances. Another just, curious thing you could do with your black box sim, you could write in any language you want. You might be working on a Unity game or Godot game or whatever, but you could write your black box sim in C++, Ruby. If you want to go nuts and create a Visual Basic black box sim, you could do that. And you could, because it's its isolated own thing. In most cases, you'd probably want to do it in the same language, but just pointing out you can't. All right, so this is the overview of what I'm going to talk about in terms of the implementation. Unfortunately, I did have to scope the talk down for budgetary and time reasons. I didn't have time to talk in depth on replays and previews, but I will hint and give you an idea of how you might implement these features. Okay, so let's talk about world state. So I'm using my own terminology with this idea of the world, but world state, I'm talking about this orange box here. So it's a single structure containing all state or variables for your entire game simulation. So let's look at an example. This is the simplest example I could think of. So here we have the player HP and the enemy HP. That is your world state. Anything that is a part of your world state, like your literal game simulation, would go into this single structure. Now, there's all sorts of ways you could organize this. But okay, I'll get into that. But first, I want to just point out this is a demonstration of Principle 3. So we have our state is completely separate of the operations that you use to modify it, and data and presentation. And this is also highly serializable. That's a very important point that leads to a lot of the other benefits. Let's just keep that in mind. Here is an example of what my world state looks like in my current game. Don't focus on this too much. I just want to give a demonstration of how I choose to organize it. I choose to organize it on like just different game features. So I have, you'll notice I have RNG is stored in the world state. So that helps with determinism. I have all my units and their stats and equipment that those units have. So I kind of have an ECS-like approach to storing my game state. You could do it however you want. I'll just give a little more example here. So here, this is my state, or sorry, my stats. So HP, defense, etc. These are, it's stored on a per unit basis. I have some code in this world state DB that handles that. But just to give you an idea, it ultimately, I'm storing a bunch of integers for the most part. I don't do floating point myself, but you can. I'm storing just a bunch of integers kind of keyed by an entity. That's what my world state is. It's all very simple, and I have very simple accessors and setters. I also have this like read-only interface that I do. But anyway, that's all kind of optional stuff you can layer on top. Okay, the second bit of this is the logic center here, what I call world command. So this is your operations on the state. So it's a self-contained bit of behavior with optional parameters, and they're initiated from player actions like clicking a button, moving a joystick, etc. Here's an example where we have a button on the screen that lets the player heal one of their units maybe once per turn. So we have world command heal. You could target a team. Maybe you can target 2 different teams, whatever, and an amount to heal by. And we have this resolve function. So it's passed in the world state. So it's showing that we're not using global state. So you could pass in any world state here. This command doesn't care what world state it's operating on. It just needs world state. Here's the target team, and we increase the HP. So this is showing principle 1, avoiding re-entrant code. So we never call, like if we have 2 world commands that heal, we would create a third kind of shared static utility function to do the healing, and both those world commands would call that shared utility. The world commands never call into each other. You're never going to create a world command inside of another world command. So it all flows from world command sort of down, top-down control. And it's also worth pointing out, we can pass in parts of the world state to a static helper function. So if we go back to this, it could be we have a static helper function that just needs to know about equipment. So we could pass in just this equipment DB instead of this whole world state. I use the term DB. It helps. It's just my concept of, these aren't like MySQL databases. They're just, classes. But anyway. Yep. And yeah, I kind of mentioned this, but we are avoiding global state and singletons. So we pass the entire world state into resolve, and that resolve function can modify any part of that it wants. And we can also serialize this. So the world command itself can be serialized. We took advantage of this for Inkbound to be able, that's how our networking worked in that game. We would serialize these world commands over the network, and we'd reconstruct the world state on the server and all the other clients based off these world commands. And for a preview system, you could imagine copying the entire world state and then applying a command on that copied version. So you wouldn't be modifying the true kind of canonical world state, you'd be modifying a copy to do some kind of preview for the player. Okay, let's talk about the presentation side. So here we have the concept of a world state change. So this is our output from that black box kind of diagram. So a world state change is a notification from a world command that state has changed. And it's used for UI purposes, VFX, animation, sound effects, whatever else. It drives all of that output of your game. And it's also worth pointing out that I only use this to emit information from the black box. So I don't use them internally. I kind of accumulate them in a list, and they kind of go out of the black box sim. I never read from them inside the black box sim. I mean, that's not against the law. You could do that, but it's just, I like to keep things very simple and separate. Okay, so here's a very simple example of a world state change. Here we are saying a unit was healed. It could have come from our world command heal. It could have come from something else in the game. Could have effect. You could have an effect that like whenever the player takes damage, they heal 1. It could come from something like that. So we have all the information that we need to know about as a response to that healing. There's one important thing I want to point out here. It's kind of hard nuance to explain, but any change in the world state you want to be fully encapsulated in these world state changes. Later on, I'll show how we're going to sequence these in animation. And because your world commands operate instantly, any change that occurs that you might need to know about in animation later on needs to be encapsulated in this world state change. I'll try and explain that better in a bit. So let's integrate this into our code. So we have our world command heal, we have our resolve function, and we've added in this list of world state changes. This is kind of our output from our black box sim. So after doing our work, we've captured some more values here. We have our new HP value, for example, previous HP. We're capturing all these values as we go. and we're putting these into the world state change, and we're adding them to the list. And that's all we're doing. So again, this goes back to principle 3, strict separation. Here we have our presentation is separate from our logic and our state. And also it's worth pointing out the presentation can only know about the world from these world state changes. I have a little asterisk because I have read from the world state directly. In some cases, I do that. In my current game, I don't, but it can be done. So demo time. Let's see if the YouTube video works. So here I'm going to run my simulation. Okay, so I think we forgot something. What happened? Well, we had our inputs, we gave them to Black Box Sim, we generated our outputs, but then we didn't do anything with the outputs. So let's talk about how we're going to actually use our outputs. So we're going to iterate over those world state changes, and we're going to display the results to the player somehow. That wasn't really a good demo, but it was sort of a joke, but also segue into this next part. So here's how we might display the world state changes. I'm kind of weird. I'm a fan of just sort of big, dumb switch case statements. So microcode has like a huge list of these cases, but you could organize this in different ways. Anyway, here we have our world state change unit healed. We have a couple UI elements here. We have a health bar for the player and the enemy, and we have this concept of combat numbers. A lot of games, if a unit takes damage, we show maybe a red number pop up above their head, or if they heal, it's a green number. So imagine this is like a UI element. So as we're parsing these world state changes, we just iterate over them in order. And here, if it's the player, we set the player health bar, we update that, and in the combat numbers, we show a healing number at that health bar position with the amount healed. So they see that they gain 3 hit points. That is the core concept of how you then use these world state changes to update the UI. But there's a detail that's actually pretty important, and that's animation. So all of this stuff right here happens immediately. When you call that world command play card and the world state changes that are generated, that all happens, you could think of that instantly. It's as fast as a computer can process. There's no concept of time or animation in the black box. It is just a computing machine. But this stuff down here, we need to make it animate over time. The player needs to be able to comprehend what's happening in the game, and animation, it turns out, is pretty important for that. So the way we could look at this is world command play card has generated, in this example, 3 world state changes. It told us that a card was played, a unit was moved, and a unit was attacked. So maybe this is a tactical card game. I always kind of go back to card games. I don't know. So that's the outcome of playing this card. And depending what card you play in the state of the world, you will get a whole different set of world state changes. So it's sort of unpredictable what's going to happen. And down here, we're going to sequence these. So card played, we're going to sequence an animation, which is, that card kind of going to the center of the screen and fizzling away. The unit moved, the character's going to move across the screen. Then we have this unit attack. So we're going to show the attacker swinging a sword, and we're going to show the attacked unit taking damage and reacting to the hit. These are kind of sequenced one after another. In practice, you'd maybe you allow the unit move animation to start while the card played animation is ending. You could sequence these in different ways. So this is kind of the way I've implemented it. My implementation on the animation side, I don't feel 100% great about. I feel like it can be improved. So I think there's work to be done there on the animation side. But that's the concept. So this is showing top-down control. You can see how it literally moves top-down. At least the way I've visualized it here. But yeah, world commands generate these world state changes, which sequence the animation. And it's all unidirectional. By the time the animations are playing, the world command and the world state changes, they're long gone. They don't exist anymore. So these animations are self-sufficient. So let's return to, if we have really great gameplay architecture, what does it give us? Determinism. So the gameplay logic is much more predictable. We've encapsulated things like RNG into that kind of world state. And so it's much easier. Things like animation and player input are often the types of things that can break determinism in your game. So we've completely separated these things. We don't care about what the player's doing with the mouse or how long exactly an animation takes. That's all output of our black box sim. Save load. So world state is centralized and highly serializable. So if you want to implement save, you can serialize that entire world state structure to JSON file, binary, whatever you want to do, and you can load it back up in a similar way. There's still a lot of details with save and load, but it is much easier when all your game state is centralized rather than being split up between all these different UI related classes, presentation classes, and gameplay classes. Networking. So the world state and world commands are highly serializable. So I talked about with Inkbound how we would serialize both when you first connect, we'd send the whole world state. It's kind of support late join. And then we would just synchronize world commands back and forth. It was super low bandwidth and efficient. And you could also do it the other way. You could reconstruct. Oh no, I'm getting ahead of myself. Sorry. Here's what I'm talking about. So with replays, it comes back to serializing again. You can serialize the world commands and the initial world state to regenerate the replay, or you could do it the opposite way. You could just store the world state changes and serialize those and drive your visuals with that. So you don't even have like a real backing black box sim. You just have the outputs of the black box sim driving. I don't know if there's a reason to do it one way or the other. I've done it the way where you save the world commands that then generate the world, but you could do it either way. And an undo redo system. I've implemented this type of thing before where at the start of the turn you save off the world state, like start a turn world state, and then if they press the undo button, you can copy over your canonical world state with that original version. There is some effort here to synchronize the game UI to that world state, so it's not free, but much easier. And a preview system, similar. Let's say I'm dragging a card to go play it. I copy the world state. I run the play card world command, and I read the world state changes. And instead of applying them like I do normally, I parse out the ones I care about. So like a unit took damage. I could accumulate how much damage that unit took, reading through all those world state changes. And I could use that. I have a special UI layer that shows damage previews, and I could use that number to show those previews. And it will be entirely accurate considering all game effects. You might have some passive relic style effects or whatever. It'll take all that into account because it's just running your normal game code. And testability, if you want to do some automated testing, you can create custom world states for tests and run world commands, verify world state changes are emitted in the way you expect. There's all sorts of stuff you could do on the testability side. And you get fewer bugs because the gameplay logic is much more predictable, and the separation helps a lot too. You know, the bug I have here is a game logic related bug. It's in my black box sim. I could fix that without having to worry about an animation as a separate bug to the one on. So that separation helps a lot. And then it's much easier to reproduce bugs. If you implement a replay system, you can have players send you replays. You could automate it even. So you get the replays. It could tell you exactly which git commit to go to generate, and then it's just a matter of running the black box sim until you generate the same error. You could much easier to reproduce bugs. So that's it. That's the concept of what planning out, having really well planned out gameplay architecture, and I wasn't able to go into depth on all these things, but I think you could understand how you would benefit from this architecture for all these reasons. So that's my talk. This is my email address, and I'm on social media. I don't check as much, but I love to talk about gameplay architecture. I kind of nerd out about this stuff. So if you have any questions or comments of any kind, please feel free to reach out. I've chatted to a few people over the years from my original Roguelike talk on Monster Train, and so I'm happy to talk to people. That's all I have. I don't know if there's time for questions. I kind of took all the time.
Excellent. It's fantastic. No, thank you. And I mean, certainly personally, I love the coming back of like, hey, I talked about something a few years ago. It's now been referenced in a bunch of projects, and I know how it went for them. Let me talk about what I learned as I continue to apply that in the real world. I always think that that's great. It's like you've got that extra tested in real world circumstances seal of approval.
Yeah, and with a few years now behind us, so.
Yeah. No, I think it's fantastic, and such a big part of games. It's one of these things I wish people had told me, because my title has ended up becoming like technical systems designer, which is a lot of just doing this. Like,
I see.
when you work on big enough teams, I gotta have a name for it. So
Yeah.
We might have time for like one quick question if anyone has one to throw
Sure.
out, but if not, then we'll we're going to give Robin another chance. But
Yeah, I'm not looking at the questions right now, so I trust you.
yeah,
to
I've
pick
got
one
it.
after.
I've got it open. If anyone wants to throw one out there, but yeah, I know serialization was coming up a lot in terms of lightweight ways to serialize and use information, which was a favorite topic. But probably it would be best if we do follow up in the breakout rooms so that we can try and give Robin another chance
Sure.
at the internet. But thank you very much, Brian, for coming back and sharing with us. And if people are able to follow up with you, that will be in the Fountain breakout room, or you kindly provided your email. So
Great.
Excellent.
Well, thanks a lot for having me.
yeah, thank you.